So this particular session, I just want to just a little bit about the how you should do the sampling and what questions comes to your mind, what type of samples you can analyze, what kind of measurement techniques will be provided will be here, what kind of application you can do. Just sir has already explained very well. But I don't have to understand about all the theory and what is the science behind this particular circular dichroisms. But when it comes to the samplings, like some of the questions from purity, then what kind of amino acids or protein or peptides, so and what kind of result we will be receiving in this particular instrument, and what we are looking for, and what should you be looking for. So that thing I will try to cover. So in that, if you have any questions or if you have already used those instruments and if you have not got the results, so we can discuss those things as well, right? So Ranjan sir has already introduced about the JASCO instruments. So this is Japanese spectroscopic company, the corporation, which is it is in 1958 we are into the scientific field. So with the first instrument we started with the IR instrument, then along with that we also had a different instrument like UV spectroscopy, Raman spectrometry, circular dichroisms, then HPLC instrument. But in last, what we can say, in the last 2 or 3 decades, we have been world leaders into the circular dichroisms. Not only circular dichroisms, we are also working on to the circular polarized luminescence, vibrational circular dichroism. So there are, if you want to work on the chiral molecules or chiral compounds, so we have those particular equipments to cater those particular requirements. Okay. So actually, I had prepared for many of the things, but sir has already covered the basic theory. So I will didn't go into the CD measurement parts and some of the applications what you can do with this instrument. So just basic information. So sir has already discussed this. What exactly the light is always a very important part. Take from your invisible spectroscopy to your mass spectrometry. So not to the Raman spectrometry and even CD microscopy. So light is play very much important roles in normal UV region to the near IRs, X-rays. So there different regions, different kind of wavelength light people have been used for their different applications. So that and for that particular reason they have developed a different instrument. So firstly, like what we are going to work on to the UV visible and NI region. So this UV visible region, so the instrument circular dichroism. So basically, we are going to work on the UV and NI region. So this is just optically active molecule. If your molecule are optically active, then you can analyze your samples very well. It includes your proteins, peptides, even natural compound as well. But in certain extent, you won't get absolute chirality, but you will get something. So we can go with the what kind of chirality is there. Obviously, point chirality. The carbon molecule is the central, then the different molecules outside. So like planars, axial and helical. So there are different kind of things. Like I said, sir says there is no limit to use this instrument for different applications. This is just overview, just as explained. Okay. So initially, like rightly, 0.1 mg per ml sample you can analyze, but the kind of assays we have, we can also go with the 20 microliter of your sample size. Just single small drop of your samples is enough to get the data of that particular sample to get secondary structure estimations. So this is basically circular dichroism people generally use for the secondary structure estimations of your proteins molecules. You know the primary proteins, primary amino acids, which is different amino acid linked with the polypeptide chains, then its secondary structure, then tertiary structures and quaternary structures. But the things what we can do with this instrument is to analyze and to characterize and quantify the structural secondary structures of molecules. When it comes to the secondary structure molecules, then your proteins and your peptides. Peptides, we generally know that more than 20 amino acids, we call them as a peptide, even 5, 6. But what kind of structure they will form? It won't be. It is sometimes to get to understand those particular molecules, we use the circular dichroisms. So this is basically design. Sir has explained actually very well about this. This is light source. This is photoelastic modulator where your light actually be converted into the light and a polarized light. This is photomultiply tubes. Okay. My point is to take this session is to know your samples very well before you go to the analysis. So whenever we go when we go to the instrumentation lab, the CD lab CD, so there are different things. What kind of samples you are going to be analyzed? What should be the source of your samples? What is the purity of your samples? So what is the pre-sampling methods where we require to get the samples to get analyzed? Then what are different measurement techniques? Like the CD, we have the JASCO, the Spectrum Manager is one of the software we use for the taking your sample analyzed, right? So there are different measurement techniques were there. So different parameters were there. So what parameter will be required? Because this circular dichroism, the instrument, the J1500 instrument, it is compatible with a different kind of assays. Like not only structural conformational studies, but you can also get understanding of the kinetics of your proteins. You have protein interaction, protein ligand interaction, ligand interaction. So those kind of things, if you want to study those particular interactions, you will be using different assays. For example, stop flow, titrimetry, then your fluorescence assays. So the different assays we can be utilized to get a different understanding about the samplings. And the last but not only the data processing, whatever data what you have get, whatever the spectra, either it will be alpha shades, beta shades or tons. When it comes to the quantifications, so how you will process those data? I mean, getting good spectra itself is a big challenge. Next, how you can get a different ratio, how you can calculate those particular ratios. So there are different softwares are there, different statistical model was there. So what is the basic understanding? So what is the basic understanding of those softwares? That I will try to cover from here. Okay, so this is the basic structures of your protein. You know, generally we can through CD we can analyze the tertiary structures, secondary structure, tertiary structures, and somewhat quaternary structures. Prosthetic group we can also analyze in different in higher regions as well. Okay. So, like I said, so in circular dichroisms, like I said, you can work from the 160 to 50 region. In this particular regions, you get the secondary structures of your protein. For example, you have alpha helix, beta sheets, and turn the quantification. So basic chromophore, like light get absorbed by these peptide bonds. Okay. So this is basically chromophores, and that actually gives the results. But when it comes to the tertiary structure analysis, like this is mostly range from the 250 to 350 regions. So this tertiary structures is basically the fingerprinting region of that particular proteins or your peptides. So in this, your aromatic amino acids like tyrosine, amine, and tryptophan. So these are the basic chromophores. So that particular amino acid basically absorb the lights, and based on that, it gives a fingerprinting region of that particular protein. So it gives this particular peaks. So every proteins you can get a tertiary structure of protein. People also study any denaturation will be there. They can also figure out depend on the intensity. If it is decreased, so they will get the tertiary structure. You can also study the prosthetic groups, right, from 350 to 500 regions in nearby near-eye regions. So these are the different things you can do with these circular dichroisms. Yeah. So next, I will say, so there are the like I said, when you get the spectra and when you get the quantification, you get alpha helix, beta sheets, and tons. So these are the this standard color. What you can say, if your protein is alpha helix, it will always look like this only. So in the positive side, there is one hump at between 190 to 93. It depends on the protein. Sometimes people get 195 as well. So it depends on that. If from 190 to 95 region, you get particular humps. And the negative side around 208 to 222 regions. So this is a particular, what you can say, alpha helix look like. So every alpha helix has to be look like this structures only, right? If your protein is beta sheets, obviously one base positive humps at the 195 200 region. Sometimes we get the 202 region as well, basic humps at. Then negative hump at around the 217 or 218. So it depends on the protein to protein. So like if your protein is complex, alpha helix also there, beta sheet also there. So this particular humps will just relocate from that 1 or 2 nanometer, it will shift. Okay, so it depends on the ratios. Then it's coils, and so you analyze your proteins. Okay, unknown samples. So for example, you get PSA as whole stream as a samples. You measure 1 mg per. When you do secondary structure analysis, 0.1 to 0.3 mg per ml samples is enough to get good CD spectra. If you want to go tertiary structure analysis, we will require 1 mg to 3 mg of cell samples for tertiary structure analysis, right? That quantity of samples will be required. So once you analyze those samples, you get a particular circular dichroism, you get a spectra. Then how the spectra is getting calculated, right? So how we will calculate this alpha helix, beta sheet and terms. So there are different softwares JASCO has provided. So initially we come up with this protein secondary structure analysis, and then newly we come up with this SATHI multivariate program. Okay. So why I'm saying that getting spectra is one part and getting analysis is second part, because spectra, getting good spectra itself is a big challenge, and then the how you will quantify. So this, for that particular reasons, in the protein secondary structure we might have seen those. We have the two models like Young's and Reid's. The Young's and Reid's, when we go to the instrument, if we have the software, I will show you definitely. The Young's and Reid's, basically these are the two scientists. Okay, the Young's, he has worked on mostly on alpha helix proteins. So whatever the protein he has analyzed, so he has published some papers, and in that the protein which widely alpha helix, so he combine those protein and he make laboratories. So similarly, the second one is the Reid's. He worked on the most of the peptides, the conformation of basically peptides. He took different kind of peptides, different variations of peptides, and he quantified the secondary structures and he make a library. And particularly those libraries we have been used to analyze our unknown protein. So what we do here, we make a statistical model out of this particular different libraries, and we use those libraries to get your unknown sample, get correlations. Okay, so how? Because we know that if your protein is alpha helix, it will always has the 2-1 hump at the positive and 2 hump at the negative sides, right? So accordingly we have created those particular statistical models, and here you just correlate your samples with that particular statistical model. So this means that having this statistical model itself is if you have the good statistical models, if the protein in which you are working out, so it will give a good predictability, right? It will give good correlation values, right? So depend on that. The limitation was when we work on this particular when we use this particular statistical library. So that's why with that considerations we come up with this SATHI multivariate program. So initially where it is 6 to 8 protein sequences, but in multivariate we included almost 26 protein sequences. And actually it is continuous process. The way we are working on different kind of proteins, we are also working on another libraries which will cater people who are working into the beta sheets proteins. Right?
Those are 26 protein sequences or structural variants?
Yeah, total structure, X-ray crystallography of those 26 protein sequences which has been included in that particular software.
Why not more? Because in PDB you can find.
Yeah, you can add more. Obviously, it is depend on what kind of protein you are working on. Why we are included 26, it at least give a basic, because although it's small, but it will cater what is the requirement of this particular to find alpha, beta, and terms. Because if we work on specific proteins, you will take that particular library. We will select those particular proteins to get a good correlations. Right. You can start with that. Even this software also include they have the facility that you can include your own protein as well. You can create your own libraries as well, right? Because since it's a correlation studies, like you must heard about the if you study the Raman library also, even you can study with the IR spectra also, you can in proteins or like this. In SATHI also we also very much depend on the this particular libraries. Even not in SATHI, but even go for your online sources as also. There are different libraries were there, right? You can study if you want to analyze your data with different libraries, get a good understanding. You can go over there as well. So it depends on what kind of protein sequence you are going to be studying, basically.
Those will be for unknown proteins.
Unknown proteins, right? So likewise, people say like, why I'm getting a different result many times. Because one day I'm analyzing one sample. There are different things where there are different parameters where during sample preparations as well, how you prepare samples, it also very much important. Like different things were there. This is just a how we create a model of how we multiply these abundance ratios and all. will not go. This is about the series model. So if you have any doubts, we can separately talk on this particular statistical model as well. Right? So in multivariate we actually give the two statistical model, this PCR and PLS. The PCR is principal component regressions and PLS is partial least square methods. So these are two different logics to get your samples get predicted. Okay. So if you analyze your samples on two different models, you will get something different. But generally what we have, why we develop this model, if you are working on this PLS model, if your protein molecules is very much similar with that, the protein molecule which is already present into your libraries. So getting good correlation will be useful for us. If you are next, once you come with this model, so the next thing, what kind of samples and the measurement things we have to be taken consideration. So you should know, so it is obviously the Lambert-Beard law. First of all, your concentration is very much important. Your path length of cuvette is very much important. And E, we call them as a molecular absorptivity. So how mole of your samples get absorbed, it depends on that. You get it's simple. What you do normal spectroscopic. In normal spectroscopic, invisible we actually use a linear light, but in the CD we actually use the circularly polarized light. Right? We analyze molecular samples. So the sample concentration is very much important. Like I said, 0.1 to 0.3 mg we generally is recommended for to get analyze your secondary structures of proteins. Then 1 to 3 mg of protein, it will be recommended to get a tertiary structure of protein. But in that case, in the secondary structure, you can go path length up to 0.1, 0.2. Like small path length, that's very much okay. If using 0.1 path length, you generally require 300 to 400 milliliter of samples. So that much of samples will be required for getting analyze your samples. Right? You can also go with the 0.2 if you have the high concentrated samples. Then what type of buffers, what type of solvent you should use, because see each and everything is matters. Like if you in the selection of solvent, that solvent should not be interfere in that particular band. Like if you're working on the UV particular 190 to 250 regions, so that particular solvent should have the limitation that would they should not absorb those particular lights. So the selection of solvent is also very much important. Then the selection of buffers, you know that the particular activity of your proteins or the stability of your protein is very much depend on your buffers, right? If you don't use buffers, sometimes over a period of time, after 5-10 minutes time, your samples get precipitated. Like they will not be in good situation to get analyzed. So like what kind of buffers also, like different buffers have the different absorptivity and different wavelengths. So we have the list, even in the laptop also, we have the CD manual. So they have listed out what kind of solvent you should use, what solvent will be having the absorptivity at particular wavelength. So what path length you should be using. So this all the details has been given into the manuals. Even the what kind of buffers, at what concentration you should be used. Because increase in concentration, like generally positive buffer has a good, they don't interfere with your your visible region if you want to on the secondary structures. But the concentration is always matter. Like we recommend the 50 millimolar it's okay. Don't go beyond that. Even sometimes people working on the different chlorine-based buffers also, so we don't recommend that because they interfere into the wavelength range, right? So different things. Yeah. So as I said, the sample concentration is very much important. The path length. So what we generally recommend that people start using, take analysis with the 0.2 mm path length of cuvette, right? See, if you started working on 0.2 path in cuvette, so sometimes if you want to reduce the buffer concentration, and if you don't want to use that, right? So certain buffers is very much required to get stabilize your proteins. But if you are not getting good result at 0.2 path length cells, then you can decrease those path length up to 0.1. Okay, so you are not decrease the concentration, but decrease in path length. So in a way, you can get a good CD spectra into that also. So you can narrow down on that particular way, right? So this is things. So whenever you get a CD spectra, there will be one you will get a CD signal, and second one will be the HT values. This HT value is generally said as it should not go beyond 700. It's like the absorption of your samples. If you have samples it is more concentrated enough, it will, the data whatever, the absorption will not be proper. So like when you go to this absorptions and transmittance, so if there is no transmittance, if you're working on the particular UV region from 190 to 160 to 250 or 31 around, so you will require this quartz cuvette. So quartz cuvette, you should use quartz cuvettes. Different path length of quartz cuvette will be there. Different quartz cuvette will be having for different applications, right? So different path length. Yeah. So start with sample preparation. Like I just said, if you're working on, if you want to take good spectra of your samples, like I said, structures of protein, in order to get, if you want to understood that if your protein is, the activity is intact, it will depend on the, if it is good in structures as well. So if you want to, before going with a different different instrument, before you study the circular dichroism of your samples, you get to know that your protein is intact, they have a good information. Like, so likewise, your protein should be pure enough to get good spectra, because other compound, other ligand also they can interfere with that particular region and they can deviate your sample, they can deviate your spectra. Okay, it won't give a good spectra, and if you don't get a good spectra, it won't correlate very well with that statistical model. So ultimately, you will get a false result many times. So like 3 to 5% change also sometime for some kind of protein is big things. Okay. So check if you're working on the fermentations, if you're expressing or if you're producing proteins. So check out the nucleic acid, because the nucleic acid also interfere, because now we also analyze the DNA, mRNA as well. So they can also interfere with the proteins. So the ratio should be 0.6. So if you're working, if you want to get purified, you can dialyze your proteins. You can remove the different ions out of it. It will get a good. Okay. So these are the different chlorine, and these are the minimum concentration you can work. It will be limitations for that. So clear solutions is must. It should not get settled on like I said, whatever the solvent you will be using is very much important. Like your protein should be it should be soluble in that particular solvent. The solubility is very much important. When it's soluble, then you can get a good analysis. It should not precipitate it. Okay, so many things get diffracted, so you won't get a good results. So this diffraction, right, scattering is generally happen if your protein is not very much stable. They form clusters. Sometimes they move and they get aggregate, and sometimes they get precipitated. So this thing has to be consideration. So whenever your sample is there, it should not be foggy. So this sample is not good. It should be clear enough to get analyzed. You can work on different buffer concentrations, different solvent systems. Okay. So this is generally happen with the absorption flattening. So if your protein is not very much, it is not solubilized enough, they may form a different aggregation, and they create a flattening. Okay. Okay. So like before, like I said, like when we work on the cuvette, like each and every component is very much important. Even in cuvette also, when you work on secondary structure estimation. Like when you work on the thermodynamics of your protein, like if you want to work on the how your protein is stable, what we figured out based on the melting temperature, right? So if you want to work on the thermal stability of your proteins, you will work on that particular part. If you working on the kinetics, you will work. So each and every time we use this cuvette. So cleaning of this cuvette is also very much important. So what we do when we work on the thermodynamics of protein, we ramp your temperature from your 30 degrees Celsius to 90 degrees Celsius. You make your samples, you get denaturation curve, right? You get melting temperature. But after that, sometimes what happens, the protein gets stick inside your cuvette. When you go for the next sample analysis, the initial samples also get hampered to next year analysis. So what kind of cleaning agent you should be used? This is Helmanex, it is detergent we actually recommend. So this is just okay. So initially, if your proteins are say water, when you use the baseline correction, so it should give a 0 dichroism, right? It should be there. If your liquid, if your water sample is given dichroism sample, or maybe your cuvette it is contaminated, so you should check before to analyze. The ST voltage is minimum, right? The ST voltage should not be there. Should not be giving absorptions like this. So like I said, the different solvents, I mentioned over just few of the solvents, but you will get a list I will share you this particular manual. So you will get a total list of your solvents with the different path length, if using different wavelengths range, how they are behaving, if they are absorbing to light or not, with what kind of keyword you will be using. So these things you will take by Weissen's specifically the limitations up to 220 regions. But phosphoric acid, this has absorption at below 190. So this is very much okay if you're working on the 200 to 250 region or 195 to 250 region. So this range we will not be having any interference. So selection of the buffer and concentration is also very much important. So this is just a basic what do you say SOP, like if you're working on a secondary structure of protein like far UV or near UV. So these are the different criteria that we will be working on this particular range. What path length you should use, what protein concentration you should use, what solvent or the UV rate. So these are the different things, and you should the distributor should not go beyond 700. So this is the thing you have to take consideration, okay, while analyzing the samples. So 1 mm path length generally accommodate around 350 to 400 ml macroliter of your samples. You can also go with the, you can also analyze the assays. We have one of the assays, micro sampling assays. So where only 20 macroliter sample is enough to get your sample analyzed. So we will get a data out of it also. Not only secondary structure confirmation, if you want to analyze the melting temperature of your protein with that particular, that amount, the small amount, that also very much possible with this instrument, because this GF 1500 is designed, this instrument, with consideration of the people and scientists should use a different assays and they get various data out of it. Okay, so when you go to the hands-on training, right? When you use Spectra Manager software to get your sample analyze and get your data process, so you will be in the measurement. You will be facing. This window will pop up in your Spectra Manager. So this is just give the information. I will just give a brief because so when you go for the parameter, this is actually more. I will go in that, but we'll go in hands-on. This is, like I said, the continuous scan and step scan. Two things. This is the DIT, how the data is integrated with your time and how it will move from every 1 nanometer. This is response scanning speed. Yeah. So thank you for the measurement. So we have also different applications as well. If you want, I can explain you, or can have next day as well.